some reason, I suddenly had the urge to sleep with my sister. All right, so welcome. I'm glad you're all laughing. I love the fact that one of the statements at the beginning of this whole event was, so we have to write a paper. Yes, you have to write a paper for everything. That's a big part of environmental work, is reporting things so that you're getting good experience. This class, I think, will serve you very, very well. So the title of my talk is, so you want to be an engineer, so didn't I. All right, you'll notice I do not have a PE behind my name. I have a QEP. That stands for Qualified Environmental Professional. I have a degree in environmental science. I did not go to school for engineering, but I kind of do engineering. But I'm not allowed to call myself an engineer because of laws. So anyway, a little bit of background. Who I am and why should you care? I'm a middle-aged white guy. That means I'm in charge of most of the world. But more importantly, I am a son, I am a brother, I am a husband, and I am a father. I'm a human being, and I have a family, and everything that we do is as a result of a family caring for us and getting us to where we are. So we never want to forget that, no matter how ambitious or how focused we are, that there's more to life than just your career. So just always remember that. I started with this sort of stuff when I was doing my internship with the Slippery Rock Watershed Coalition, the SRWC. I was doing monitoring and some lab analysis, and that's when I learned about passive treatment. And passive treatment is the vast majority of what I'm involved with. That's dealing with mine drainage and building essentially wetlands to treat that mine drainage. I earned my Bachelor of Science in Environmental Science from Slippery Rock University in 1996. It had one of the oldest environmental science programs in the country, and ergo the world. It started in the early 70s with an actual degree called environmental science. Right after college, I had the opportunity to be a drummer in a band, so I was kind of a semi-professional musician and also hardware store clerk. The band was breaking up and I decided I had to get a real job, and so I started volunteering with the Slippery Rock Watershed Coalition, and that's where I got kind of reintroduced with some professionals in the field, and I actually began my career by volunteering for a consulting company that filled out mine permits. They were doing work with the Slippery Rock Watershed Coalition, but the majority of their business was mine permit applications, so permit work, paperwork. And I just basically said, hey, I got Wednesdays off from the hardware store. I want to learn about what you guys are doing. Can I just come down and work for free? And so I did. And so that gave me experience. It got me out, meeting people, and shortly thereafter they offered me a part-time job. Eventually that turned into a full-time job. My business, and then my future business partner who I work for, Margaret Dunn, her business partner at the time decided to retire. She looked at me and said, hey, you want to start a business? I said, sure. I was 23 years old. I really didn't have anything to lose, quite literally. So we moved into her basement, bought a computer, and off we went. I also, at that same time, she had started a nonprofit, Stream Restoration Incorporated. I became a director and secretary-treasurer for Stream Restoration Incorporated, which is SRI. That same year I got married, and my wife's family built a barn on the property, so I built a barn, started a business, got married, all at basically the age of 24. So I kind of started life in a big hurry. Anyway, so experience, things I have done. This is a picture of our office from a number of years ago. This is myself diligently working at my desk. This is Sean Busser, who's our biologist. Cliff Denholm, who's another environmental scientist that I went to school with. We really started our business by doing mine permit preparation for coal and limestone surface mines. Okay, not underground mines. Basically they dig down, expose the coal, dig it out of the ground, and sell it. We were working for some local mining companies, Miracle Mining and Quality Aggregates, and as a two-person consulting company initially, that was plenty to do. Because of the impact of mine drainage, we also got into watershed assessment and restoration plans, passive treatment design, active treatment design, and eventually things kind of snowballed and we got into doing micro hydroelectric design build, and also part of what we do is basically, when we started in this, there was no textbook for passive treatment. You basically kind of made it up as you went along, and so some of the technology that's used out there, we were involved in the development of that technology. So surface mine permitting, just to give you a little flavor, you have a mining operator. This is John Stilley, the owner of Miracle Mining. We have DEP regulators, we have lawyers involved. There's myself many, many years ago. There's Margaret Dunn. And we're having a meeting out in the field to discuss a proposed coal mine. That's part of consulting, is meeting with people. So learning how to communicate and write reports and pay attention when people are talking is a very important skill. And I'm glad that you're developing those skills in a seminar like this, okay, when you have to listen to people other than your professors to pick up on what they're saying. Just to give you a little flavor, I mean, have any of you actually been out onto a mine site anywhere at any time? Kelsey, you can raise your hand. Okay, we got just a handful of people. When you hear a mine site, some people, relate that to something, as a dramatic impact on the landscape. And a lot of abandoned mines do have a dramatic impact on the landscape. But in 1977, they passed a law that required surface mine operators to reclaim their mines, and that they would have to be responsible for any bad water that would come off of those mines. So a lot of technology was developed with surface mining, and permits that used to literally just be 3 or 4 pages back in the late 70s, early 80s, are now hundreds and hundreds of pages long. There's a lot of testing, and there's a lot of work and science that goes into surface mining. So as environmental engineers, you may be involved in some of the aspects that are involved in doing surface mine permits. Basically, this was the first permit that I ever worked on. It's the Teich mine up in Butler County. There was a mining company that was kind of going out of business. They hadn't been doing a whole lot of mining. This is a high wall. This is about 40 to 50 feet high. The coal seam is just at the bottom, so they would just remove the overburden. That's the rocks on top of the coal is the overburden. They move that off. That'd be a great quiz word to pick up on your reports. It's overburden. What is that? So they basically dig down to get to the coal, and here's the mine actually reactivated, and you see this is like a D9 bulldozer that's pushing the dirt out of the way to get down to the coal. Then they pick up the coal and load it on trucks and sell it up to a power plant. This is 2001 was when they were actively mining it. In 2003, this is reclaimed. If you drive by that site right now, you wouldn't be able to tell it's a surface mine. It just looks like any agricultural field, because the reclamation was done correctly in accordance with current laws and regulations. So just want to give you a flavor for that. Now, what's interesting, you can't quite pick up, the resolution's not that great. This feature right here on the high wall is kind of unusual. I'll blow it up, I don't think you'll be able to really see it, but that's actually a goat. That's living on a ledge about 20 feet off of the ground on this mine. So that's an actual goat. And he lived on the surface mine. So we destroyed goat habitat when we reclaimed this mine. So anyway, watershed assessments and restoration plans. Here's another picture of Cliff here, and this is Cliff and I out sampling at a site. This is actually out at the AMD and Art site here in Vittendale. We're out taking a look at that passive treatment system. But collecting samples. Measurements are important. Getting good data. If you're going to engineer something, you have to have a basis for your design. You need to know how much water you have to treat and what is the pollutant load that you have to remove. So measurement is important. Collecting good data is very, very important. And also, good flow measurements are very important with a lot of mine drainage design work. There's so many times I have a lot of samples but no flow data, and people ask us to come up with a treatment design, and it's very, very difficult. We've done a number of assessments and restoration plans over the years. The first big one we did was for the Montour Run Watershed Association in 2003. This is another one we did for the federal government, Blacks Creek Restoration Plan. A lot of this work is grant funded, working with nonprofit groups. So that's part of what we do, is actually go out in the field and identify problems. And that's kind of what I wanted to go to school for, is to go out in the field, because I did a shadow study when I was in high school at an environmental engineering firm, and I saw a bunch of guys sitting at a desk working on paper and computers. And just to kind of go back, this is what I ended up doing with my environmental science degree. I'm sitting at a desk with a computer working on plans. I'm doing environmental engineering essentially. But that's what I do is passive treatment of abandoned mine drainage. Now with abandoned mine drainage, that's discharges that come off of mine sites. By the way, how long do I have until what time?
The class ends at 3, so if we have a few minutes for questions.
Cool. So passive treatment systems is what I love. They're essentially wetlands. So what we do is we'll go out to a site, during our assessment phase, and we'll go identify the problem. Okay, here's a diffuse seep zone coming off of a abandoned surface mine. We went out and we actually dug a trench, collected the water, put a pipe in there, measured the flow for just about a year to assess the extent of the water pollution problem. We then came up with a passive treatment design for the site. We then started clearing off the site, got all the dead trees and the muck out of the way. Using the same equipment that we use for surface mining, we were using it for installing a passive treatment system. Passive treatment, kind of the rough definition of passive treatment is that you don't use chemicals and you don't use electricity, generally speaking. You're just using natural processes, natural materials in order to neutralize acid if it's there, also to remove pollutants such as iron, aluminum, and manganese. Those are the three big metals that we concern ourselves with most passive treatment systems, especially in Pennsylvania. Elsewhere, there's other issues that I'll talk about a little later in my presentation. But basically, we built some ponds, we put a network of pipe at the bottom of the ponds, put in limestone and compost, and then we planted the wetlands. This is actually Slippery Rock University ecology class that came out and was involved in planting some of these wetlands. This is DeSalle Phase 1, this is DeSalle Phase 2, and we basically just collected drainage in a French drain, directed into two ponds that operate in parallel into a settling pond, wetland, and then a horizontal flow bed, and then it goes out into the stream. And these are both located in the very headwaters of Slippery Rock Creek. The drainage divide is not too far outside of this photograph. And so these had a huge impact on the headwaters of Slippery Rock Creek because most of the drainage in the creek was coming from old abandoned surface mines and was heavily polluted. And by installing these passive systems, we were able to restore the quality of the stream so that it was, the stream basically had a pH that was below 4, couldn't really support aquatic life. We brought that pH above a 6 and took out most of the metals that were emanating from this area of Butler County. All right, another thing that we're involved in at Biomost is we actually have gotten into active treatment design. That's where you use chemicals and limestone. And we started getting into active treatment with non-electrified active treatment systems where they actually use water wheels to auger in lime. But then we've since branched out into actually doing kind of full-blown classic active treatment systems for mine drainage treatment. Same problem. We have a seep that's polluting a stream, and one of the reasons why we decided to go with an active treatment system at this site is that the seep was coming out very close to the stream, and there wasn't enough topographic relief to be able to put in all the components that we needed to for a passive treatment. Plus, this site, the flow gets up to about 500 gallons a minute, which makes the size of a passive treatment system much, much larger. With a passive treatment system, you basically have to build it for the maximum flow because you can't turn up rocks. You have to put in all the rocks in the wetland size you need right up front for it to be effective. Where with a chemical-based treatment system, you can always turn up the amount of lime. You still need enough settling time in your ponds, but if the flow comes up or the acidity level comes up, you can increase the amount of chemical feed that you use. But I mean, it's a big construction project. It's an industrial type construction project. This is a 40-foot high, 12-foot diameter steel silo. That's where the hydrated lime is stored. And then there's a automated augering system located at the base of that silo. And then this is actually the mixing tank that we're putting in. We were using an airlift mixing tank. This is a 10-foot by 10-foot by 12-foot deep tank. It comes in multiple sections. We had to use a 90-ton crane to pick it up and set it down into the hole. And then at the end, this is what the treatment system looks like with your lime silo. Your mixing tank is right in front of the truck. It's down in the ground, and then it comes through a pipe, through a flume, so we can measure flow. And then it goes into a settling pond with a baffle curtain, and there's a series of 2 settling ponds. This is the first one, that's the second one, and then it discharges out to the stream. And with this system, we actually have an automatic pH controller. We have a pH probe right at the outlet of the first pond. That controls the speed which the lime is fed, and we also have an ultrasonic water level meter on this flume so that we can continually read the flow. We can actually pull the site up on my cell phone and know how much flow and what the pH is right now at any time. So it's kind of neat. Another thing that we got into is micro hydroelectric. This is a treatment plant. This is the Antrim treatment plant up in Tioga County, where there was a large underground mine that was mined back as early as the 1830s through about the 1940s, and then it was surface mined. It was remined through surface mining, and a mining company became responsible for the discharge, so they built this active treatment plant, which they're using lime, and then instead of settling pond, they're using a clarifier, because the flow rate of this site was up to 2,000 gallons a minute. You can remove a lot more metals in a clarifier because it's an upflow type system than you can in a settling pond in the same type of footprint. So basically the water comes into the plant, it's neutralized with the lime, flows out to the clarifier, flows up through the clarifier, and the clean water was discharged out to the stream. There was a gentleman at the Department of Environmental Protection who was involved with overseeing this treatment plant, and he wanted to put a micro hydro turbine on this plant because they owned property that dropped almost 200 feet down over the mountainside, and with 2,000 gallons a minute and almost 200 feet of drop, you can generate a good deal of electricity. And so we put in a proposal to do a design build on micro hydroelectric, and basically all we did was we put in a small pond after the clarifier and extended an 18-inch diameter high-density polyethylene pipe down over the hill, down to a powerhouse that was constructed at the base of their property. There was still another 200 foot plus of drop down below their property down to the stream, but this is as far as they own. So we constructed a powerhouse, which was just a concrete shed that the 18-inch pipe extends from the clarifier down to the powerhouse, comes in the backside here, and then we split the flow into two different micro hydroelectric turbines. And all a turbine is an electric motor running backwards. I mean, there's a little bit finer nuances to the wiring, but it's an electric motor running backwards. We're taking the mechanical energy of the water coming out of the nozzle and spinning an electric motor to generate electricity versus a pump, which you take an electric motor, put in electricity to physically move the water. So it's basically just a pump running backwards to generate electricity. This was the first micro hydroelectric system that used mine drainage that was connected to the electric grid. And so this was the first. We actually had to get a license from the Federal Energy Regulatory Commission, or FERC, for these turbines. So you can see this powerhouse. This is about 12 foot by 12 foot. And these turbines, this is only a 27 horsepower electric motor that we have here. We had to get the same permit that you would get if you built the Hoover Dam. Yeah. And when the FERC folks came out from, they're actually based out of New York City in this area, they came out and asked to see my dam. And I was like, we don't have a dam. They're like, well, where are you getting your water? I'm like, I'm getting it from an underground mine. What is that? So getting out and seeing things and seeing different things is an important part of education. You may have a specific interest, field that you want to focus on. That's great. But to broaden your horizons, take the opportunities that you have, especially during your college careers, go out and see other things is a really important thing. Because if you have a broader understanding, you don't have to be the PE engineer from the Federal Regulatory Commission asking what's an underground mine. He had no idea what an underground mine was. So I explained that to him, and when the Dam Safety Commission part of FERC sends us our paperwork every year, we just say no dam and send it back. But every year they send us a piece of paper asking how our dam is doing, and we say we don't have one, and every year they say okay. So those reports you're writing, that's a good exercise to get in. I'm not saying all paperwork's totally meaningless, but some of it seems that way at times. But don't get discouraged. Now, one of the more interesting parts of this project, this was a design build. This is actually me on the excavator. This is just a little Bobcat excavator, a little 5-ton excavator, and we're dropping down over the hill. This is over a 2-to-1 slope that we're taking this 18-inch pipe and we had to put it in a trench. So we literally chained our pickup truck to a tree, and we put a winch on the hitch of the pickup truck, and then we're cabling down with the excavator so that we wouldn't slide uncontrolled down the hill. So I learned that in my aquatics plant class, how to do that. But that was a lot of fun. It was an exciting day. But we got it in successfully, and everything got hooked up, and we're generating electricity. We got our license, and everything is working up there. This was one of the highlights of the things I've done so far in my career. All right. Other thing I want to talk about is new treatment technology, and this I alluded to. We got into active treatment with doing some more low-tech solutions on active treatment systems. And what we have here is this is just a 30-inch diameter pipe with a cap on the end. That is a mix well, okay? And people might ask what a mix well is. It is just a piece of pipe that we put down into the ground, and then we drop water down the center of it, and then we drop lime in the top of it, and it improves the mixing efficiency of lime. I actually showed this, I came up with a drawing, I showed it to a couple different mine drainage treatment gurus. They both said, that's not going to work. But the DEP was asking us to come up with a way to improve lime efficiency at one of their treatment sites where they didn't have access to electricity. So I said, well, it's basically kind of the same thing as a diversion well, which was something that was invented decades ago over in Scandinavia, where you had acid rain coming off the European continent. A lot of granitic soils up in Scandinavia where they didn't have limestone to buffer the acid rain, so you had very acidic streams. Didn't have metals in it, but basically you dump limestone in this pipe, and the water comes to the bottom, kind of fluidizes the limestone chips, and it neutralizes the acidity. Doing that with mine drainage can kind of be problematic because you have to have somebody out there shoveling in that limestone all the time. And so that was where my mind kind of tripped out, saying, well, we have these augers that are feeding lime all the time. What if we drop that lime down into basically a diversion well and used it to grind up this calcium oxide, which is one of the treatment chemicals we use. And one of the problems with calcium oxide is it doesn't dissolve very readily, so you have to grind it down. And if you don't grind it, what will happen is those unreacted particles will just go down into your settling pond. So you're wasting chemical, and you have a whole bunch of material, inert material, or actually unreacted material, that you have to pump out as sludge. So you're wasting money, and you're increasing your sludge costs. So we came up with this idea of the mix well, and I was working with just a brilliant man, Mr. Bruce Levitt, who's since passed away. And he's the one that resurrected the whole idea of tromps, okay? The reason why any of you in this room even know what a tromp is because of Bruce Levitt, okay? And Bruce Levitt came to our office. He was all excited about this thing he had seen when he had gone on a field trip to Canada during his spring break, was when he saw the tromp that inspired his work, okay? So instead of going to Fort Lauderdale and doing those things, those Fort Lauderdale things, he and his mining engineering club got in vans and drove north into Canada for their spring break. They briefly drove by the Ragged Chutes Tromp air compressor, which was this massive thing, which the downlet pipe of the Ragged Chutes mine is 300 feet tall, and the outlet is 270 feet tall, and the separation chamber at the bottom is 1,000 feet long. He saw that as an undergrad. They just kind of drove by, learned about it a little bit, sat in the back of his mind. Years afterward, he was working on mine drainage problems. One of the issues we can have is lack of aeration, and we don't have enough physical drop to just do cascade type aeration. And so the light bulb went off. He said, I want to build a tromp. He applied for a grant to do some research on tromps and basically build. They didn't fund the grant, so he built one anyway in his backyard. And he got excited about it because it was working. He drove the entire office out there one afternoon. We went out there, we got excited about it, and we went out on a mine site and built the first tromp to be used for mine drainage treatment ever in Fayette County, Pennsylvania. This tromp is actually is installed in between just outside of Tunnelton, West Virginia, right here. And so Bruce's idea of using a tromp for aeration, during the same project where I developed the idea for the mix well, I was talking to Bruce about it, and he's like, well, let's make an airlift mixing tank and power it with a trough. I'm like, what is that? That sounds interesting. And basically an airlift mixing tank, it's same sort of thing, you just have, this is an 8 foot by 8 foot diameter tank that's 10 feet deep. And this is a 12-inch diameter PVC pipe that's just supported off the bottom with 3 little stainless steel legs. It's about that far off the bottom. Air line comes down and discharges just inside the bottom of that pipe. The bubbles come out, reduces the density of the water. That water starts to flow upward. It gets displaced by heavier water, by non-aerated water, denser water that comes in at the bottom. Okay, so the water comes in at the bottom, comes up this pipe, and then comes out the top. And using just about 4 CFM of air, we can circulate about 1,000 gallons a minute of water in this mixing tank. With no moving parts. What happens, and at this site it's kind of neat because we take, the water goes through the mix well, comes down a channel into the A mixer tank, then the effluent of the A mixer tank goes into the trompe, and the trompe discharges down into the pond. And so this is completely, this is one of those kind of like perpetual energy machines that literally there's no energy input other than falling water. The water comes out, goes down the trompe, compressed air is captured in these air chambers, one at the inlet, one on the outlet side. This is the outlet of the trompe. There's about 4 feet of difference from the inlet to the outlet. This is 4-inch PVC pipe down to 6-inch PVC pipe, up at 4-inch, comes out, and it generates the compressed air to power the airlift. This is us installing it. This is the mix well being put in the ground. People don't get excited about the mix well, even though this does about 60% of the mixing of this dual-step mixing process. I have another picture that I'll show you here. But this is the tank here, the A mixer tank. So that 12-inch diameter pipe is in the center of that thing. This is the trompe, just looking from the other side. These black pipes are coming up, and they are the air lines coming from the air chambers going into the mixer tank. And so the pipe comes out, goes down through the trompe, and then the discharge of the trompe goes down into the settling pond. This is a picture of the actual mix well itself. We pull off a little bit of the water to run a tipping bucket inside the silo, so it distributes the lime. It falls down into this sluice, which is just a piece of culvert pipe cut in half. That drops it down into that mix well. Then the rest of the water, which is about 120 gallons a minute, comes in the 6-inch pipe, goes down the center. So the heavy particulates get retained in the bottom until they have a chance to dissolve and grind. It's an autogenous grinder. They just grind against themselves, and the finer particulates eventually make themselves up and make their way up out of the mix well. And so we reduce the particle size of those lime, of that calcium oxide lime, and then the finer lime particles go down a short section of channel, then into the A mixer. And so this is a picture of the A mixer tank, taken just above water level. So that's the air line going down. That 12-inch pipe is submerged just a few centimeters below the top of the water, and it just circulates. You can see that we're getting like really good mixing with 0 electricity and 0 moving parts. And yeah, that's the picture. I'm sorry. This is a picture of Bruce Levitt. He's the guy that resurrected the idea of trompes. These things were developed in the 17th century to be used to power blast furnaces in the iron making process. And he saw them being used to power underground mining equipment, pneumatic, like air tools, back in the turn of the century, back in the 1890s, 1910, 1920, that time. And they built these giant air compressors in South America, in Canada, the United States, essentially all over the world. And that technology has basically been forgotten. There's still an operating trompe up in Peterborough, Canada, where they actually use the compressed air to open and shut a lock and dam. So it's actually, this technology is still being used that was installed over 100 years ago, designed back without the advent of electricity or that sort of thing. I mean, it's pretty amazing stuff. And there's a lot of possibilities for this. And you can generate about 4 CFM of air for every 100 gallons a minute that you have, which is kind of neat. So to talk a little bit about what my company, Vimos, does, we describe ourselves as mining and reclamation services. We do assessment, design, and permitting, and that's kind of the consulting. That's how we got our start, is with the consulting. And then these treatment systems that we designed, we put them on permitted mine sites where clients had to meet permit effluent limits. make sure that they don't discharge water with too much iron or too high of acidity into the stream. So they asked us to do the monitoring and the maintenance of these passive treatment systems. So we ended up renting some equipment and eventually bought some equipment and started doing some minor construction type work for the maintenance of these passive treatment systems. And that led into doing full-blown construction jobs. The micro hydroelectric was the first real construction job we did, and then we've since built some large, full-scale passive treatment systems here in Pennsylvania and also in Oklahoma. I'll be talking about the Oklahoma project here shortly. This is very shortly. Here's the Southeast Commerce Passive Treatment System. This is a very exciting project for me to be involved in. I was very honored because one of the guys that literally wrote one of the early benchmark papers on passive treatment is Dr. Robert Nairn, whom has instructed a number of professors in this room. I think you know Dr. Bill Strohsnyder and postdoc Julie LeBar. And he has a great graduate program, makes master students. My environmental engineer, Buck, who's spoken at the seminar in the past. And these two guys, I mean, this is, Dr. Nairn is kind of, he started a center, Center for Watersheds. So that's kind of like, he taught Dr. Strohsnyder. Dr. Strohsnyder is learning what Dr. Nairn taught him and building on it here, great. And so like you're like first generation Nairn, and then like you guys are like third generation, like kind of, third generation Nairn. So anyway, he had been working down in Oklahoma. This is Commerce, Oklahoma, home of Mickey Mantle. This is actually the Mickey Mantle memorial statue right here. This is Commerce High School. This is the high school here, football field, baseball field. And about 10 years ago, they installed one of the first passive treatment systems in Tar Creek. Actually, that was the first passive treatment system in Tar Creek. This is a Mayor Ranch site. And up here, there was a reclamation project that was done by the state of Oklahoma. There were two subsidence holes, red hole and green hole, that they backfilled. But there was about 100 gallons a minute coming out of those holes. When they backfill them, the water has to come out somewhere. Okay, so that's a good engineering practice. Like, if you have flowing water in a natural system, if you don't attend to that or provide a way for it to flow and continue to do what it wants to do, it will find a way out. And after they backfilled these holes, they actually dug a pond, they used fresh dirt and backfilled those holes, and then there was just a whole mess of red water that came out along this area uncontrolled. So what the city and the state of Oklahoma the city of Commerce, state of Oklahoma came in, put in a French drain system and piped it down to a culvert right here. And that's what the University of Oklahoma started monitoring in order to eventually put in a passive treatment system. This is actually a subsidence. After they backfilled the first two holes, Dr. Nairn went up there on on Thursday, I believe, came up and saw that there was a new subsidence hole that had formed. So they had to fence off the area, and there was just red water coming out down below this area. So they had another subsidence hole to deal with. So one of the things Dr. Nairn did is he used his grad students to monitor the Southeast Commerce Passive Treatment System. I'm not sure if you can really recognize this guy right here, but that is Dr. William Strohsnyder measuring the flow. They actually piped the 100 gallon a minute discharge into the side of the culvert so you couldn't see it coming out anywhere. And then this culvert extends below the Commerce High School football field. And that's Dr. Strohsnyder during his grad research days monitoring the Southeast Commerce discharge right there. I'm not sure who that is. I don't think it's your wife. Okay. So this is that freshwater pond. This is where the holes were backfilled up here. There were mine workings that were mapped, kind of mapped, in this area here. So we decided to keep the passive treatment system off of this area. And we were really tight on space, but this is the passive treatment system design that we came up with. It's basically an oxidation pond to remove the major pollutant, which is iron, which is about 130, 140 milligrams per liter of iron, but there was also about 6 or 7 parts of zinc, about a part of lead in this water, and then some cadmium and some of the nasties that we normally don't have to worry about or think about in Pennsylvania. But down here, because this was the lead and zinc mining district, those pollutants are present in the water. The water flows around baffle curtains and through a wetland shelf into a vertical flow bioreactor, which is just a mix of primarily wood chips and spent mushroom compost. That flows into a re-aeration pond, another wetland shelf, a final polishing pond, and then back out to the stream. So these are engineering designs. This is, learn AutoCAD. Everybody, you have to learn your drafting programs, learn GIS. We use those regularly. Like every day I have 4 computers with AutoCAD on them and they all get used. It's a really important design tool, so if you have a chance to take an AutoCAD class, it would be ridiculous not to if you want to be an environmental engineer, if you want to do any sort of engineering. So this is just an elevation schematic showing the water flowing through the system coming out from the collection system into the oxidation pond, wetland shelf, vertical flow bioreactor, into the re-aeration and polishing units, and then out to the stream. And these are some of the details that we had as part of our design. So that is what we do. We come up with the ideas. We have to visualize what those pipes will look like, what they'll be doing, and then make a drawing that will be able to convey that to a contractor, which in this case was essentially ourselves, to be able to construct the treatment system. This is some photos of the actual construction. We did the layout. This is Dr. Russell Dutnell, who's an adjunct professor at the University of Oklahoma. He helped us out. We had to keep the client happy. This is Dr. Bob Nairn. So, we had to do our job and also keep our client happy, which is an important thing. Actually do the earthwork and the construction. This is me putting in one of the outlet pipes to the inlet structure. There's an inlet structure right over here. And the pipe was actually located below the water level, so we had to get in there and figure that out. And then as part of this system, we wanted to do aeration step, but to put in a trunk, you typically need about 1 meter of drop. That's about the entire topographic relief in the state of Oklahoma is about 1 meter. So we weren't able to put in a trunk, but we were able to put in a small 3,000 watt solar system to power some small electric blowers that are used for aeration in the Southeast Commerce Passive Treatment System. This is just a picture of Buck. This is as we're deploying these floating, what I call lift aerators. They're floating airlift. So they operate under the same principle as the A-mixer tank, where you have a center pipe, bubbling air at the bottom, lifting the water up. We're putting that in the oxidation pond. These are the baffle curtains. These are PVC Z-pilings that we used. The site was so tight that we couldn't use up treatment area for embankment, so we had to come up with some creative ways to overcome the limited space. And then this is a picture of the 12-panel, 3,000 watt solar-powered system that we have a battery bank inside the shed, electric blowers. One blower runs the aerators in the final polishing unit, the oxidation ponds. The other blower is actually used as a vacuum because when you use a bioreactor, when you're reacting sulfate with bacteria, you get hydrogen sulfide gas. It stinks a lot. We're literally right, that is the high school football stadium right there. And we were right next to it. So we came up with some new ideas on how to control that hydrogen sulfide gas, and this is actually an activated carbon tank that gets sucked up and goes through an activated carbon tank. So this is what the system looks like from the air. This is our temporary dirt stockpile area, the oxidation ponds, into the vertical flow bioreactor, and then the final unit, and then out to the stream and down underneath high school property. So one of the things that I enjoy is being able to share what I know, okay? And it's a great opportunity. Actually, Dr. Strohsnyder called me up one time, Tim, you need to hire a student of mine. She needs an internship. You need to do it. I'm like, I'm too busy. I don't want to have blah, blah, blah. He's like, just do it. So I did. So I listened to your professor. And so I hired Kelsey for a summer internship. She got to run some equipment, help install some piping. This is at the Jennings Environmental Education Center, so she was our version 1.0 SFU intern. She worked out fairly well. She worked hard, and she got to do a variety of things. This is version 2.0, which is Josh English. He is working hard work, so that's the other thing I want you to ask. Adventure, try something new. When you're going to school for engineering, but Kelsey got to learn what Schedule 40 pipe really meant because she installed Schedule 40 PVC pipe. Same thing with Josh, he got to run equipment. This is actually constructing a full-scale passive treatment system. It was a smaller treatment system, but still a full-scale passive treatment system on a bond forfeiture site, an old surface mine in Pennsylvania. This is, okay, now we have Courage. This is Cam, which I have a guy working for me now called Cal. And having Cam this summer and then hiring a guy named Cal, it's very, very difficult. I'm going to call you Cal and call him Cam. It's just weird. So this is Cam locating a outlet pipe at a passive treatment system just outside of Penn Run, PA. And so, Ryan, who's our main O&M guy, lifted Cam out so he could find the pipe, and so he's out there. And I mean, it's a 10-foot drop, I think, on either side of that pipe.
Yeah.
But he was finding they eventually found the pipe, opened up, and got the passive treatment system working. And then we also have a postdoc internship program at Biomos. We had our version XP, Dr. Julie Lamar, who she got out there and actually, this is her just like removing old silk fence at a treatment site where we're doing some upgrades to it. And this is her running our track loader. This is her being stuck, I think, was that within 5 minutes?
Like 10.
Okay, 10 minutes of running the track loader. But she has her seatbelt on. She's in a rollover protection system. So she's perfectly safe, everybody. No harm came to Julie. But she was a huge help the fall before she started the postdoc program here at St. Francis. Enjoyed having her around. We have a partnership. Biomos, based on Bill's vision, we have a partnership with St. Francis. We're doing work with your center. And this is just a picture of Bill and Julie when they were undergrads or grad students at OU at a conference up in Gillette, Wyoming. So they got out and went to conferences to meet people, and that's how I got to know Bill intimately. This is us actually dancing in a 23 cubic yard dragline bucket that was used as for surface mining coal in Wyoming. And that's kind of how we developed a relationship that allowed, has benefited my company by giving me a nice steady stream of good quality, hard-working interns that are willing to get in the mud and do real work. And also allowed us to further our programs and like what other work that we do at Biomos and Stream Restoration Incorporated. So the next step, one of the things that Dr. Wagner asked me to talk about, kind of what's next for Biomos. The big thing for us is we want to maintain our reputation for quality work. There are engineering firms out there that are known for not so great quality work, and that's unfortunate. As an engineer, you have a code of ethics to follow. There are people that are out there that really, based on what they design, don't work because they don't know what they're talking about, essentially. And you can run into that. I mean, that's a real thing. There are engineering firms out there that do that. And I mean, we've kind of made it up as we've gone along, and we've tried new things that we weren't sure were going to work. But one of the things that I think differentiates us is that we share what we know. We go to conferences, 2 to 3 of them a year, at a considerable expense for a little 7-person company. And we do presentations, we do papers, we tell people what we did right, what didn't work so great, so that others can learn. Because there's so much mine drainage out there. There's a lot of people that have to work on it for us to really be able to tackle the problem. One of the things that I see, I want to maintain a small business. I don't want to get big. I want to be the AMD-A team. I want to be able to be flexible and small enough to react and come up with creative ideas. You get into a big firm, and it gets a little bit more like the Army. But those have their place, and kind of where I see myself as the AMD-A team. One-stop shop for AMD issues. We can do assessment, we can do design, we can do permitting, and we can do construction and operation maintenance. And we have a number of clients that we basically handle their AMD problems. Also nurture partnership efforts like St. Francis University, and then there's other nonprofits that we work with that we try to expand what we do, not by having more staff at Biomos or SRI, but actually working with others and kind of using one of those buzzwords of building capacity. And like I said, is share what we learn. One of the biggest regrets I had in my college career is that I didn't skip enough class. Okay? It might sound a little off, but what I mean by that is I didn't go out enough and see things and go to conferences, take volunteer opportunities, take that spring break trip to Canada. Take those opportunities. That's what you need to do, because when I look at a resume, yeah, I see your GPA. You graduated from good school, that's great, whatever. What I look for is the other things. I look for, okay, are you an Eagle Scout? That shows dedication and commitment. Did you play on some sort of intramural team or sports team that shows additional hard work and cooperation? Did you participate in the student chapter of ASMAR? Those things are what stand out on a resume, is the extra stuff. And that's what Dr. Strohsnyder does. He doesn't have to take time off from his job and his family to fly 24 hours to South America, dragging a bunch of undergrad students down to Bolivia. He does that so that you guys have opportunities, and he's helping and he's expanding what you guys can learn. And you guys are very fortunate to have a group of people here that are willing to go that extra mile. And my professor that I had got involved in the Slippery Rock Watershed Coalition. That's how I got into doing what I did. Unfortunately, his predecessor, his successor, doesn't do that so much. And so, if I had to point to somebody that was interested in AMD, I'd point them to St. Francis, because you guys are out there doing things, and it's awesome. And this is Dr. Nairn, blessing the work of the Slippery Rock Watershed Coalition. And so, looking ahead, we're looking down into a line check. So anyway, I think I've gotten myself just a little bit past, and now it's your turn to go out there and do stuff. You might recognize some people here. This is Hannah Patton, who organized this group to go up and help plan a wetland on a passive treatment system. And so this is what I'm talking about, is taking those opportunities. Yeah, there's going to be that party Friday night, but we go out and plan a wetland before you go there. All right. Any questions?
Yeah, it's time, but so you have to go, but any questions?